All right, so every electronic device you own, I mean everything from your phone to your car, runs on one single fundamental rule. It's kind of like the secret code that tells electricity how to behave inside a circuit. And today, we're going to crack that code. We're talking about Ohm's law.
So the big question is, how do we actually get electricity to do what we want it to do? Well, the secret is in this kind of fascinating dance between three key players. You've got voltage, think of that as the push, then there's current, that's the flow, and finally resistance, which is the pushback. And trust me, if you can master how these three interact, you can build just about anything.
Okay, so first things first, let's really see how these three forces, voltage, current, and resistance, play off each other. The best way to think about it? Imagine electricity is like water flowing through a pipe. Now, what do you think happens if you crank up the pressure, or what if you pinch the pipe?
And this slide shows it all, beautifully. It reveals two really fundamental truths. Okay, first on the left, if you keep the pipe the same size, that's your constant resistance, and you crank up the water pressure, that's the voltage, what happens? You get more flow, right? More current. They're directly related. But now look at the right side. If you keep the pressure the same and pinch that hose, you're increasing the resistance, well, the flow of current slows down to just a trickle. That's what we call an inverse relationship.
So this totally predictable relationship, it was perfectly described by the physicist George Ohm, and that's why it's the bedrock principle we now call Ohm's law. It's really just a formal way of saying what we just saw. More push from voltage gets you more current, and more push back from resistance, well, that gets you less current. Simple as that.
And check out this graph. It shows us something incredibly powerful. For any given resistor, the relationship between voltage and current is, well, it's perfectly predictable. It's a straight line. That means if you double the voltage, you can bet you're going to get exactly double the current. That perfect linearity, that's the real magic of Ohm's law.
Okay, now let's flip it around. What if we keep the voltage steady? Well, then the relationship between current and resistance forms this classic inverse curve you see here. And notice something really important. See how just a small amount of resistance causes a huge drop in the current at the beginning? This is an absolutely crucial concept for controlling how much current flows in a circuit. Look closer. Doubling the resistance from 20 to 40 ohms, it cuts the current precisely in half.
All right, so this is the part where the concept turns into a practical tool. We can actually express Ohm's law with a super simple set of formulas. You'll see that these three equations are really just different ways of looking at the same thing, and together they make up our essential toolkit for analyzing pretty much any circuit.
Here they are. You can think of this as the Ohm's law magic triangle. The bottom line is, if you know any two of these values, you can always solve for the third one. So, enough theory, let's actually put this toolkit to work with some real examples.
Okay, first up, calculating current. And just as a quick reminder, current is the actual flow of electricity, and we measure it in amperes, or amps for short. So let's see how we can figure it out when we already know the voltage and the resistance.
And the formula? It's super simple, and actually really intuitive when you think about it. The current that's flowing is just equal to the voltage that's pushing it, divided by the resistance that's holding it back. Push divided by pushback.
Okay, hold on. Before we jump into the math, we absolutely have to talk about prefixes. Because in the real world of electronics, you're almost never going to see a plain ohm or a plain amp. Nope. You're going to see stuff like kiloohms, milliamps, and microamps. And trust me, getting these prefixes down isn't just a good idea. It's totally essential if you want to avoid making some pretty big mistakes.
All right, let's look at our first example here. So imagine you've got a 100-volt source, and it's powering a 220-ohm resistor. The question is, how much current is actually flowing through it? We just plug the numbers right into our formula. 100 volts divided by 220 ohms, that gives us 0.455 amps, or more commonly, we just call that 455 milliamps.
Now check this out. What happens when we use a huge resistor? We've got 25 volts, but this time it's trying to push through 4.7 megaohms. And just to be clear, that's 4.7 million ohms. So what's the result? Well, the current slows down to a crawl, just 5.32 microamps. This is a perfect example of how you can use a big resistor to seriously limit the flow of current.
Okay, next up, let's just rearrange that formula. Let's say you know exactly how much current you need to flow through a component, and you already know what its resistance is. The question then becomes, what voltage do you need to apply to make that happen?
Well, this time we just multiply. The voltage you're going to need is simply the current you want multiplied by the resistance it has to push through. By the way, this is also what people mean when they talk about calculating the voltage drop across a resistor.
So, let's say you're designing something, and it requires a pretty hefty 5 amps of current to go through a 100 ohm heating element. What kind of power source are you going to need for that? The math tells us everything. 5 amps times 100 ohms, yep, you're going to need a pretty powerful 500 volt source to pull that off.
This is a brilliant example. This is exactly why getting those prefixes is so useful. We're multiplying 10 milliamps by 3.3 kilo ohms. Now think about it. Milli is 10 to the negative 3, and kilo is 10 to the positive 3. So what happens? They cancel each other out perfectly. All you have to do is multiply 10 by 3.3, and you get a nice clean 33 volts. Super slick.
And finally, we've got the third part of our toolkit. So imagine you're digging through a drawer of parts and you find some mystery component. You have no idea what its resistance is. How can you figure it out? It's actually really simple. If you can measure the voltage across it and the current going through it, Ohm's law will tell you exactly what it is.
So, here's the last tool in our kit. Resistance is just the ratio of the voltage across component to the current that's flowing through it. In other words, R equals V divided by I.
Let's make this practical. Say you're messing around with your car's lighting circuit. You hook up a headlight to the 12-volt battery, and you put your meter on it, and it reads 3.08 amps. So what's the headlight's actual resistance? All you got to do is divide 12 volts by 3.08 amps, and boom, you find out it's 3.90 ohms.
And let's do one last example with those prefixes, just to hammer it home. We apply 150 volts, and we measure a really tiny current, just 4.55 milliamps. Now here's a handy trick. Whenever you divide volts by milliamps, your answer is going to come out in kilo ohms. So 150 divided by 4.55 gives us, you guessed it, 33 kilo ohms.
And there you have it. That's it. We've just put together the complete foundational toolkit you need to understand and analyze simple circuits.
These three formulas, they really are the key to everything. They unlock that fundamental relationship between voltage, current, and resistance. If you can get these down, really master them, you can solve for any unknown in a basic DC circuit. Period.
Well, that is where electronics gets really, really interesting. It's what opens the door to the entire world of semiconductors. Things like diodes and transistors. These are components that don't have that nice, straight-line relationship, and they're what make all of our modern technology possible. But that's a story for another time.